My name is Aranza Isabel Cab, and in this presentation I will be discussing the life cycle of stars. There are 7 main stages in the life cycle of a star, which we will be discussing more in depth in the following slides. The life expectancy of individual stars, however, will vary according to their mass, which generally also determines its temperature, color, and luminosity. This process can go from millions to billions of years. The lower the mass and temperature, the longer the star's lifespan. For example, if we actually take a look here at the main sequence, right, and we take a look at the red dwarfs, which are located at the lowest temperature and the lowest luminosity, red dwarfs usually live the longest, while if we go up the main sequence, right, and we go past our sun, reach these stars that are greater in mass, we see that the temperature becomes higher and so does the luminosity. These stars, their life expectancy actually decreases as they go up the main sequence. So our sun, which is here in with the yellow stars, its lifespan is around average. And we can see over here we have supergiants and red giants, which are actually stars towards the final stages of their life cycles. So once these die, they will either explode into giant waves of energy to anything surrounding them, or they will start shedding their outer layers, eventually becoming white dwarfs, and then which in turn will eventually fade out at some point. So the first stage of a star's life is, well, its birth in a molecular cloud. A molecular cloud is a type of nebula, which is a swirling cloud composed of interstellar dust and gases of elements such as hydrogen and helium. There are 2 types of nebulae. One is formed after the explosion of a star in the end of its lifetime, while the other, which is the molecular cloud we are referring to right now, is often referred to as a star nursery. Why? Because it is located in a primary site for star formation. Here, although dust and gas is spread out, gravity slowly starts pulling these particles together, forming into a dense clump. This clump of dust is actually called the protostar, which is the next stage of what we could consider now our immature star, becoming increasingly packed by the process of accretion, which will later also influence its mass. The clump eventually becomes so dense that any light is actually blocked from visibility. As it reaches this compact form, both the temperature and pressure of its center increase. So basically, what we have is a core that is becoming increasingly hot and building pressure as the accretion keeps going and the dust and gas keeps coming inward via gravity, right? Which later it'll actually collapse into itself. But right now, what we have is a hot core surrounded by um, gas and dust in a cloud, in a dense cloud that will actually cover up the light from the core. So we cannot visibly see the light yet. Um, However, once it reaches around 10 million degrees Celsius, right, the star will ignite nuclear fusion. Furthermore, it will start producing extremely powerful winds that clear up the gas and particles that previously covered it, revealing its light for the first time in the following stage, which, as we can see here, is the T-Tauri phase. And here, if we actually take a look at the image, we can see that the core is now exposed because of the wind that pushed back the dust and gas, which is over here in the circumstellar disk, right? So during this stage is the first time where the light emitted from stars is visible from the photosphere, which is the visible outermost layer of a star. At this point, the process of accretion comes to an end, making the photosphere into the source's radiation. T-Tauri stars are still incredibly young, being less than 10 million years old, but they still produce strong X-rays through coronal activity, actually X-rays similar to those that our sun produces. Their circumstellar disks, which are the rings of dust and gas we can observe in the image, provide astronomers with theories about planet formation and migration, since occasionally they will find some gaps in the disks which could potentially signal an interruption by a large planet. So a planet could pass by here and it will clear up an area which will leave small gaps in the disk. After this comes the main sequence, which is the longest stage by far, since it can last billions of years. Because it lasts so long and has reached a stable balance of gravity pushing inward and the pressure of nuclear fusion pushing outwards, in fact, 90% of all stars are currently in this stage, including our sun. However, in the transition to this stage, there are some stars that do not reach the stage of nuclear fusion due to their small bodies and end up becoming brown dwarfs, never igniting. On the other hand, stars with sufficient mass that successfully reach nuclear fusion are placed in a graph of the sequence based on their temperature and luminosity, which are generally dependent on their mass. So here we can see the main sequence of star and the relationship between temperature, luminosity, and color. So we can see as the graph moves towards the left, the temperature increases. As the graph moves up, the luminosity increases. And as the stars, right, they increase in temperature and luminosity, the color shifts from red to blue. We have what are called red dwarfs on the bottom right corner as the main sequence increases towards the left. We can see that the higher the temperature, right, the higher the luminosity and the color shift from red to blue. Our sun is part of the sequence, lying somewhere around the middle right here. Now, because the smaller, cooler stars are using up their hydrogen in a more gradual manner, that means that the dimmer the star, the longer its lifespan. Above the main sequence, we can see the supergiants and the red giants, which is the next stage of a star's life. From there, they will either explode or extinguish into white dwarfs. So, once a star has used up most of its hydrogen, the stable balance of gravity pushing inward and the pressure of nuclear fusion pushing outwards becomes disrupted. The energy becomes more intense and the pressure increases. As the core contracts, the outer layers expand and cool down. This leads to the star's transformation into either a red giant or a supernova. A supergiant, sorry. It can reach sizes up to 100 times its original size. As it keeps growing, the core becomes more and more unstable, causing intense solar winds and some mass ejections before reaching the end of their cycle. Actually, these mass ejections are what will lead to the shedding of the outer layers, right? So the last stage of a star's life cycle is, of course, its death. This occurs in one of two ways. Either the star starts shedding its outer layers as a result of this mass ejections, right, that I mentioned previously, that it goes through, eventually becomes a planetary nebula. It will eventually become planetary nebula. Or if it is a more massive star, the outer layers are expelled all at once in a violent and humongous explosion called a supernova. So this will send waves of energy, just like in the picture, just going all over around the explosion. They will reach really far. If the star forms into a planetary nebula, right, by shedding its outermost layers, it won't explode. It'll eventually extinguish and become a white dwarf, cooling and fading over billions of years. However, if the star does go through a supernova, it will release incredible amounts of energy, you can see here, onto its surroundings, possibly triggering the formation of new stars by creating more, the nebula creates more molecular clouds, right? So it possibly triggers the formation of new stars, or it can also create heavy elements such as gold. So in conclusion, a star's life cycle takes place throughout billions of years, going from dust and gas coming together to collapsing onto itself and becoming hotter, to clearing up the space surrounding and becoming finally visible, to arriving at its longest stage where it continues performing nuclear fusion in a balanced way until its hydrogen eventually runs out, causing its cores to contract and its layers to expand, and finally ending in either an explosion of energy or slowly fading away. So these are my works cited, and thank you so much for listening.